Therefore, P of 0, which is not 0, you remember, multiply by P of 0, inverted, is also in my ideal. So 1 is in my ideal, right? So if I have any f, then f multiply 1, 1 is in the ideal, must be my ideal. So that's your maximal ideal. And this artificial, as you think, example is rather general actually. This is a good example of maximal polynomial, of maximal ideal. That's, and this is rather numerical, you know, free term, no, not enough numerical. Okay, so these are ideals. So what we discussed here, I think, did we have a hearing about isomorphism or something?
I think that was in the previous section.
Maybe it was in previous section, and then I won't ask you. So this discussion, did it make sort of better or make it worse or what?
No, it made sense.
Okay,
This is easier.
so this is section 3. Now what about section 4? Section 4 is completely different. Completely different. Unfortunately, they're not connected. So section 4 tells you the following.
Wait a minute, I thought quotient fields were the same thing. It's related to the idea of a factor set, right?
Nope.
I thought quotient set and factor set were interchangeable. Now it's just
Nope.
that we're not talking about set, we're talking about field. Okay.
There is a word quotient in both, but we are not using term quotient rings, we're using term fractions. Factor rings, I'm sorry. Factor rings, quotient rings.
I thought quotient and factor were interchangeable.
No, they're not. They're not. Anyway, so all section 4 is glorified theory of rational numbers. There is nothing more in it. That's just rational numbers in greater generality. That's it. So, what is the question? If I have a ring, can I put it in a reasonable way inside of a field? Now, you remember the difference between ring and field? There is something which I can do in the field, which I cannot do in the ring.
Multiplicative inverse.
Every non-zero element has non-multiplicative inverse. So it means that in the fields I can divide. Of course, I'm not stupid enough to divide by 0. By 0 I can. But by anything else. Okay. So the question is, first question is reasonable question. For which ring in principle it can be possible? What would be necessary condition? Answer. If I have a ring in which product of two non-zero elements is equal to 0, then just forget it. You understand? I cannot embed a ring like this in a field. Because if I have in a field product of two elements to be 0, and each of these elements is not 0, it's impossible. Right? Because every non-zero element has multiplicative reciprocal. And so this product has multiplicative reciprocal, while 0 doesn't have it. Right? You cannot invert 0. Well, we proved it with you many times. That if A and B belong to the field, and A multiplied B is 0, then either A is 0 or B is 0. And proof is very straightforward. If A is not 0, multiply both sides by inverse of A. This is product of 0 with something. At this moment, we already know that 0 multiplied by anything is 0. On the other hand, this product, because it's associative, I can reduce it as B. So if A is not 0 in this product, then B must be 0. If A is 0, we're also done. So this is a necessary condition, therefore. If I have a ring in which product of two non-zero elements is 0, I cannot embed it in the field, so I shouldn't make something. Try to make something which is impossible. But there is another question. Suppose I don't have such elements, and we consider specially rings with these properties, they have a special name. How the rings are called which don't have 0 divisors? There was a special name.
Integral domain.
What?
Integral domain.
Integral domain, exactly. So, that's just terminology, which means I have a ring without 0 divisors. the claim is that this necessary condition is also sufficient. That is, any integral domain can be embedded in a field. And after that, we had rather tedious proof of it. But basically, if you, instead of writing what we wrote with you, A, comma, B in brackets, and B is not zero, if you just decide to write these symbols as A divided by B, whatever it means. Now, what is the problem here? We're in an abstract situation. It's not like you're cutting an apple in halves. You don't have an apple to cut in halves, you understand? When you're cutting apple in half, you have this 1/2, you can sort of use your intuition. Here you have something which is not number, who knows what it is. Here you have again something. So, but nevertheless, these symbols, you can think about them as new symbols. And operations are like this. So, for example, A divided by 1 is A. Seems like reasonable thing, right? And if you take AB and you multiply both numerator and denominator by the same quantity, result doesn't change. Yeah. So, all familiar properties of fractions. Okay? And then out of these symbols, you are making new object, a ring. How you are making it? A divided by B plus C divided by D. I hope you know the formula. BD plus BC divided by BD. And something for multiplication, which you know. It turns out that new object is also a ring in which you also have division. Because what is reciprocal for AB? B over A. Now, why we need more than that? Because we need to be really careful, you know, we're proving theorem in great generality. We don't have any idea what are these elements from which this integral domain. So we have just to watch every step not to make a mistake. You understand? We shouldn't get carried away. It seems like very simple position, nevertheless we should do everything carefully, you know, in order to avoid mistakes. So that's what is this section all about, nothing else. Okay. So that's rather natural, but this being careful is important in mathematics because it happened that there were theorems which were proved, accepted as proved, and after, say, 10 years, 20 years, mistakes were found. And not just mistakes which could be improved, crucial mistakes, so that the theorems went back to being problems. Okay? So in mathematics, you really have to cross all T's and dot all I's. You cannot get carried through. Okay? Now, there are some people with certain abilities which, say, write papers on their own books where all statements are correct, though proofs not necessarily. Okay? They have some vision. Okay? Well, of course, then other people will look at this paper, look at this theorem, supply it with correct proof, but it's also, these people maybe are even more important than people who actually prove things because they feel what is correct, what is wrong. There was one very famous mathematician, René Thom, who told something like this, I don't know, but about any idiot can prove a theorem, big deal. To invent a theorem, that's what is really interesting. To invent the right question, that's, and it's a little bit overboard, but there is something in this.
Did we ever talk about a theorem that said that like any two consecutive integers are relatively prime?
Hmm?
Did we ever talk about a theorem that said any two consecutive integers are relatively prime?
Which integers?
Any two consecutive integers.
Well, it's obvious.
Did we ever talk about it?
I don't think so, but why? What is the difference of two consecutive integers?
One.
One. Is one relatively prime to anything?
No.
What do you mean no? What is greatest common divisor and and anything else?
Yeah, one's relative to
One.
my
It's
dad.
always one.
Right.
So that's it, because we discussed with you that greatest common divisor of A and B is always equal to greatest common divisor of this improved thing. Right?
Yeah.
Because if something divides both A and B, it divides A and this difference. Right? Because if B is divisible by D and A is divisible by D, then the difference is divisible by D. Right?
Yeah.
On the other hand, if something divides these two numbers, it also divides B. Because B is this number plus this number. So that was a basis for Euclidean algorithm for looking for greatest common divisor. So you're saying, did we prove this?
No, I just wondered what you talked about, because I thought maybe I invented that theorem, but then I looked it up on the web, and it turns out somebody else already thought of it.
But that's called proof of it, right? Because n plus 1 minus n is 1. Okay, but think about it. Suppose there is number d which divides this one and this one.
Mm-hmm.
Then this number d divides their difference. Right? If two numbers are divisible by d, then their sum is divisible by d, and their difference is divisible by d. But since difference of these two numbers is 1, then 1 is divisible by d. And what is divisible? By which numbers 1 is
Only
divisible? Only by 1. That's it. Well, if you want, also by negative 1. So this is chapter 5 for us. That's it. You know, that's it. Of course, I can ask you some pesky questions. So let's go back to groups. And you had a list of questions? Did you prepare a list of questions?
Can I be in a group with Justin? Wait, what are we doing?
Well, I'll go home, you know. I'll
I
just
thought we were
go.
forming groups.
Okay,
Can we do a problem?
sure. Whatever, look. I'm here to help you to learn the material. Whatever you want, I will do. Theoretically, we covered all of it.
Yes.
But
yes.
practically now, you know, in order to... And I'm looking at your homeworks, you know, I'm not...
Oh, did we get our?
Tomorrow I'll bring, well, tomorrow, which is Tuesday, which is not quite tomorrow, I'll bring both of them. Again, I checked one of them, I didn't check another one, I didn't have time to put it in the list, you know, to collect it in
No,
my computer.
I want now.
You want it now. Why do you want it now? You want to ask a question, ask a question. By the way, did you give me the last homework?
Yes.
The last one?
I think we decided he was caught up.
He caught up.
Oh, he wasn't here.
Yeah, okay.
Oh,
No, last time he just
was-
walked out, so we
yeah.
discussed it.
Yes,
Anyway,
yeah.
so go ahead.
Okay.
Ask your problems.
114, can we do number 19?
Page 114,
Yes. Is subgroup? I mean, if somebody else wants something different, then you can.
114, 114.
Mm-hmm.
Okay. Let's look at this, number 19. We have a group, we have an element. We have something which is called centralizer of A. Show that this is a subgroup, show that cyclic group generated by A belongs to it, compute in some particular case, whatever, compute, whatever. Okay.
114.
What's the session?
Oh, I'm sorry, 3.2.
3.2, yeah. Okay.
I don't know if it was a homework problem. though.
It's not a homework problem, what's the big deal? Homework problem, not a homework problem.
Number 19.
Okay,
It's
so-
interesting, I-
You will, again, so those of you who will stick up to 543, you will have more of this. So you have an element A in the group G. Definition. Centralizer of A is collection of all G's in G such that AG is equal to GA. Which is to say, commute with A. Centralizer.
Center and centralizer.
Central and centralizer are relative notions,
They're not the same.
not the same. Because, of course, any
Oh, center
element
is the
of the
side.
center
It's a centralizer.
commute with A, belongs to the centralizer. So, centralizer of A contains center of your group. Because center of the group commutes with everything, right?
Huh.
That's elements in the center commute with everything, so they commute with this A. Now, in fact, you have this relation. Center of G, think about it, is intersection of all centralizers. Because what is centralizer of A? Elements which commute with A. Intersection of all centralizers, elements which commute with everything. Because they belong to centralizer of every element, right? Okay. So what are the questions? Natural question, is it a subgroup? So what should we check for a subset to be subgroup? Closure. Closure. Okay. So I have G1, G2 belong to centralizer of A. I want somehow to deduce that this product belongs to centralizer of A. Now, how can I do it? There is only one way for it. Through definition, right? The way centralizer. So what should I check? Is it true that this equality is correct? Of course, since I'm multiplying G1, G2, this is the way to put brackets. Is this true? I'm saying, sure. Just recall that your multiplication is associative. Rewrite this like this, right? Use that G2 is in the centralizer and rewrite it like this. I'll do it really slow. Okay? So far so good? Now put brackets like this. Correct? Associative operation. That's my feeble attempt to write A. Use the G1 as in the centralizer and rewrite it as G1 by G2. Right? And then put this equality, because operation is associative. So instead of proving it directly, I proved it like this, using two facts. Fundamental fact that my operation is associative, and definition of centralizer using that these both elements were on the centralizer. That's it. Okay? Ebony, what's wrong?
I'm thinking, I'm just making sure I understand it.
I'm starting with this, and I start rewriting it, using the fact that I can put brackets
Okay.
wherever I please, you know, and then using the G1 and G2 commute with it. That's it.
Okay.
Of course, if you have this equality, then multiplying it by G inverse on both sides, you get A G inverse is G inverse A, which means that G inverse falls in its centralizer. That's it. So that's why it's a subgroup. You remember, we already did it several times, just multiplying G inverse here and here. And cancel G and G. So that's a subgroup. Okay.
I think I get the rest of it now that you did A though.
Yeah.
So you
The
don't have
fact
to-
that A cyclic subgroup generated by a centralizer is just statement that A in power I commute with A. A in power I by A is A in power I plus 1, no matter how you write it.
Okay.
So that's easy. What is the else? Compute centralizer of A for particular case in S3 for cycle 1 to 3. Actually, you did more than that in a homework recently. You computed centralizer in SN for a full cycle. You remember there was this question? Show that if a transformation commute with full cycle, if tau 1, 2, and so on, n commute with this cycle, then tau is the power of this cycle. Remember you had this homework? It was one of the homework problems. Yeah. So because of that, tau belongs to cyclic subgroup generated by sigma, if this is sigma. And so centralizer of sigma is just power zero. Now, it answers question about 1 to 3. It doesn't answer question about 1, 2 in S3. of just two cycle. But this we know from our research of S3 that only itself commutes with it. Because when you remember, you have these two elements, A and B, A cube is identity, it's this three cycle, B square is identity, it's two cycle. And AB is equal to BA squared. So A and B don't commute, right? Because AB is not equal to BA, it's equal to BA squared. So that's about it. Yeah, but centralizers are important, and you will have a chance in 543 to use them a lot. Other questions? Other questions? Other questions? Yes.
You mentioned in the past that like when we talk about a like S3 or whatever, or like a group
Yes.
with 3 elements, like you
No,
figure out
S3 has 6 elements.
S3 has 6 elements. Well, you've talked about a group with 3 elements and stuff. Like when we first talked about groups, you just like built a couple, and like you made it sound like there were only like any group with only 1, 2, 3, 4 elements, whatever, looked like this.
Okay, yeah. So that's indeed the case. And of course, for small numbers, for you, it's not so hard. So for 1 element, you understand. For 2 and for 3, it's now maybe understanding of more general nature. You know by now, I hope, that any group of prime order, if the size of a group is given, is a finite group, and the size of this group is given by prime number, this is cyclic group which is isomorphic to ZP.
Huh.
Where it comes from? From Lagrange theorem. If it has a proper subgroup, then we have a contradiction with Lagrange theorem, because what Lagrange theorem tells us?
Divisor. Order.
Size of a subgroup divides size of a group. If size of a group is prime number, then we have just 2 possibilities to divide it. By 1, well, it's just identity, or by everything. So if you take in such a group any element which is not identity, consider, you did it in homework actually, consider a cyclic subgroup generated by this element, it must be all of it. So a group of prime size which is given by prime number is necessarily cyclic. And if it's cyclic, of course, it's just ZP. What else? Because it's just identity A square all the way up to n power p minus 1, n power p is identity, it's the same as ZP. Right? Identity goes to 0, A goes to 1, A squared goes to 2. Okay, so that was easy. 4,
What was the last thing you said?
that any cyclic group of size P, or for this matter of size n, is isomorphic to Zn. Right? What is a cyclic group of size n? Generated by element A. It has identity element, A square, A cube, all the way up to n power n minus 1. And the n power n is identity. Then if you take bijection between this group and Zn,